Okay, good morning everybody. I'd like to introduce you to Marten Rauschenberg. He's an entrepreneur, researcher and system architect from Berlin. He's going to talk about brain-machine interfaces and the impact on our health, life and society.
Yeah, good morning everybody. I welcome you to this little morning session here. I hope the topic may wake you up all right. For a while now I have been researching brain-computer interfaces or brain-machine interfaces, and just because I think it's a very fascinating topic. Now, since the deeper I go into the material, I realize that we're actually very close to some kind of society change at large. What I once thought is impossible now seems feasible. With this technology, we are standing exactly where we are standing in the year 2000 with mobile phones. Now, less than 20 years ago, everybody got one in their pocket, and it's almost unthinkable to not have it anymore. They have been arguably the biggest possible disruption in the last decades in human history, and BMI could possibly be the same. However, when I go around between tech people, and I do that a lot as a founder, which is my day job, I do not see this topic discussed very often. And many people that I talk to are actually rather surprised by the impact. That's why I'm now creating uploadme.org, an open source information platform with a journalistic approach for easy access to the idea of putting computers together with brains. This talk is now the first approach to bring this topic a little bit into the presence of people. In the following keynote, I'd like to give you a compact version and get you up to speed on brain-machine interfaces. Controlling brains with machines or controlling machines with brains is actually a problem that scientists have been looking at for quite a while already. Let's go through some of the experience. Already in '68, Dr. Delago, a Spanish scientist, built a device that is called a stimoceiver and put it into the cortex of a bull in Cordoba. He could push a button on his radio transmitter and the raging bull, which instantly stopped.
Electronic mind control research is not new. A scientific milestone in this area came in the 1960s when Dr. Jose Delgado demonstrated remote control over a charging bull. By connecting a radio antenna to electrodes inserted into the bull's brain, Delgado proved that the animal's aggressive impulses could be thwarted by electronically manipulating the bull's muscle reflexes.
Do you realize the fantastic possibilities if from the outside we could modify the inside? Could we give messages to the inside?
The same scientist later also worked with non-invasive methods in brain control for monkeys. However, the world didn't quite like the idea of computer-controlled brain that much, and his funding drained out in the end of '70s. In the following, scientists focused more on reading and understanding signals from the brain. Within the '80s, we were already able to read signals from a group of cells and process them and make predictions about what they're supposed to mean. We could, for example, see neurons firing in monkeys and then know what kind of movement he would do. Interesting to mention is also Dr. Phil Kennedy. He developed new electrodes. With them, he was able in 1996 already to let the first patient with locked-in syndrome talk to his beloved ones on a virtual keyboard, only using his mind. Dr. Kennedy later went so far that he implanted the device in his own head and ran around with it for 2 years, recording brain activity during speech. Now, these days, his company is decoding the data and is trying to develop something that they call silent speech, where a subject only thinks the words and a computer would actually speak it out. Then in 2004, Dr. Rainer Goebel from University of Maastricht conducted an experiment with MRIs. Two participants playing Pong against each other in real time without using any hands, obviously, and obviously also no implants. A little bit heavier hardware to carry around, though. In this experiment, almost 10 years later, Dr. Nicolelis, another pioneer actually in the field, used invasive brain implants in mice. His team set up 2 chambers to measure behavior. The first chamber in Durham, North Carolina, where the university is located. The second chamber in a Brazilian neuroscience institute in Natal. Those 2 locations are 7,000 kilometers in distance. The boxes contain each 1 mouse with a brain-machine interface implant and are connected to the internet. Every box got 2 levers with LEDs above it. Both mice have been trained to push these levers when they see an LED on top of the lever. As a reward, they get a sip of water. The mouse that is called encoder here will see only 1 light flashing up, so he knows which button to press to get his reward. The other mouse, the decoder, will actually have 2 lights flashing up, so naturally he doesn't know which button to press. But since the encoder knows the correct answer and the brain is connected to the decoder is now able to push the correct lever instead. Dr. Nicolelis made a nice video where he explains what's going on there.
Well, this is a little movie that shows to you what I just described. I'm going to play it, you can watch, and I'm going to just go you play by play, what happens in this. So you see now the 2 animals in 2 different behavior boxes. And we have one trial now where the encoder sees a light that refers to the left bar.
Is it understandable?
And presses the bar and gets its reward. Well, now the brain signal of this animal is being transmitted to the decoder, who doesn't have an indication of the lights because they're both on. So at this point, the decoder presses the correct lever, gets the reward, and the encoder gets a supplemental reward. So this is another trial showing on the right lever, the light showed up, the animal got it, the encoder is transmitting the information to the decoder is now decoding the message, press the right bar, and gets the reward. So they are collaborating. They are doing a communication through a brain-to-brain interface. Well,
the experiment was conducted with about 70% correct answers from the mouse, which obviously is way above chance. What we essentially see in this experiment is that it was possible to transfer a piece of information in form of a thought from one animal to another. He also later shows experiments where one mouse uses his whiskers and the sensory input of the whiskers were transferred to the other mouse, and the other mouse was behaving according to this whisker sensory input. What that showed was that not only it's possible to transfer thoughts, but also sensory input. And yeah, that was in 2013. These days, we are using these techniques already very frequently in humans. These processes are called deep brain stimulation, DBS, and there's a whole range of diseases that we can cure or treat with that. Here's a list. The first FDA approval for DBS actually happened already in 1997. So this technology already came a long way, and in an area that doesn't really touch consumers' input, so you probably haven't heard much about that. Mostly used are closed loops treatments, therapies, which means the patient got these 2 electrodes in the brain. They go pretty deep down, and the sensors measure brain activities. And as long as the brain activity is normal, nothing happens. Once the brain activity is kind of like unnormal or abnormal, then it stimulates the brain. The patients got these 2 electrodes in their head and 1 generator here, where you can basically program that thing. But the problem with this setup is that the electrodes obviously are very big, they're clunky, and they're not soft like the brain. And obviously also they trigger quite a large area of neurons because of their big size. Newer FDA-approved devices are working now with 12 electrodes. Also, there are devices that are called Utah arrays. They look like this, where hundreds of electrodes penetrate the brain. However, all of these are stiff and area-bound, damage patient's brain easily, and bear many other side effects. Research for this starts now to actually move out of university labs into the labs of venture capital-driven startups. There are many, but probably the best known so far is Neuralink, a startup in San Francisco that was founded by Elon Musk. The last 2 years they have been busy working, tackling the problem in multidisciplinary ways. First, they looked at the size and the material of the electrodes. They managed to build a layer-by-layer approach, which is a little bit like 3D printing, those electrodes. And the electrodes are no wider than 10 microns. That is 1/10 of a human hair that you see next to it. And it's about as wide as a red blood cell. Also, the chip is very small. Now, where they have so fine hairs of electrodes that they need to place in the brain, they can't do that by hand anymore. So they developed a robot that places the electrodes with a tiny needle that is only 24 microns in size. Here we have Dr. McDougall, head surgeons at Neuralink, explaining how it works.
Neuralink developed a tool that we're extremely proud of, the robotic inserter. Inspired by designs conceived of in labs here in the Bay at UCSF and Berkeley, we developed this robot that can rapidly and precisely insert hundreds of individual threads representing thousands of distinct electrodes into the cortex in less than an hour. This tool allows a surgeon to aim between the blood vessels that cover the surface of the brain with micron scale precision. The region of the brain shown in this video represents only a few millimeters of surface of the brain. As you can see, the brain's surface moves with the heartbeat and breathing. The robot tracks and adjusts for this movement. Using this tool, we can greatly reduce the risk of harming cortical vessels and causing bleeding. Here, the robot is selecting individual electrode threads and placing them into the brain in the pre-planned location with remarkable accuracy and repeatability. Using this system, we've been able to rapidly place thousands of electrodes into the cortex without causing noticeable bleeding.
Now they got the electrodes and the chips in the brain. Each of these chips has 1,024 channels, which means 1,024 electrodes measure brain signals all the time. They claim they can have up to 10 sensors in one brain, which means that they will have more than 10,000 sensor electrodes giving input of brain activity constantly. To understand this data, the company needs very strong machine learning algorithms to cope with that. all sensors are connected to an inductive coil that sits right behind the ear, which then is actually magnetically connected to a wearable device that is called the link. The link contains the battery. So if you take it off, the whole thing shuts down. It also contains a Bluetooth sender that you can connect with your mobile phone, and then you can use your mobile phone to update firmware or control the device. As an alternative for Neuralink's implants, I would also like to show you Polina Anikeva and her lab at MIT. Their approach is to try to figure out a way how to communicate with the brain wirelessly, to get rid of the problems and side effects due to neural implants. The idea is that neurons not only fire by electrical and chemical impulses, but also mechanically, by heat. Paulina's lab is working on a liquid material that is conductive and creates small heat points when triggered. This liquid is injected into the brain. Now, with these magnetic nanoparticles between the brain cells, she can induct small charges and then trigger individual neurons without the device inside the brain.
And then we conducted a very simple experiment. We take neurons that are sensitive to heat, and we sprinkle those nanoparticles in their vicinity, and then we apply magnetic field to the entire environment without sticking any electrodes into the system. And what you can see here is, on one side you have neurons that sense heat, other neurons do not sense heat, and when we apply magnetic field, the parts that are sensitive to heat starts to flash. It means it's being active. And in this case, there's no wires, nothing invasive. We are applying magnetic field to the whole system. And of course, we can not only do it in a dish, we can also do it in live subjects, in this case mice, who in this case become completely indistinguishable from normal mice, but you place them into magnetic field and their brain lights up, specifically ventral tegmental area, where we have injected the particles and where the neurons have been sensitized to heat. So now we have a way to modulate neural activity completely wirelessly, non-invasively, without any external hardware, using only magnetic fields.
Obviously, these are hundreds, out there are like hundreds of startups and experiments and like fascinating people to listen to. It's too much to show it all now. I will come up with a website that's called uploadme.org, which is basically an information platform for all of these things. So check it out in a couple of days and find out more. The rest of the time, I would now like to talk about the future. I think we all have a basic idea now about where we are standing in terms of medical devices, but especially companies like private companies like Neuralink are actually also targeting the consumer market as well. And in the following, I would like to dive into some of the applications that we could see in this market, most of which are actually still due during our lifetime. The first application that we will see is an app store for all kinds of analytics that we can do based on deep brain readings and deep brain stimulations. Now we got all these neurons firing and we get all the signals from the brain, but we don't really know how to use them and want to conduct more research on it, and that's what it's for. Yes, companies like Neuralink already have their own software to run their devices basically, but as we all know, the real deal is always in the data. So there's a reason why Google is bigger than Intel, right? These app stores will then open doors to thousands of developers who start building business models, data ideas, and things around these devices. With each of them, we will learn more about the brain, the transcoding ML processes will become rapidly better, toolkits and libraries will emerge, and sooner or later, building an app for your brain will be as easy as building a landing page today. The next thing the world has waited for is using a computer without a device like keyboard, mouse, phones, and yeah, sorry Siri, also voice. Data input will be a lot faster when we can submit data directly from the brain than rather tapping or typing. One way of approaching this is the silent speech that we have seen with Phil Kennedy earlier. Basically, what we do is we're saying the words inside our minds, but we don't form the words with our mouth and tongue. But there are also other approaches as well that are more direct and don't use the detour over speech. Think about how artists will, for example, be able to create digital art intuitively. Or think about how quickly the gaming industry will jump on it when you can think of an intuitive first shooter person game, for example, or other crazy games that you can think of. Also, maybe think about your pilot who is steering your plane and who could now actually feel the plane as if it were his own body. This will be the first real killer app with these devices. Because people who don't have a BMI of any form during that time will work much less efficient. Adoption of this first technology will be very quick. Some employers will not accept people without BMI anymore for certain jobs. New generations will jump up on it quickly, and older generations will just follow. Same as we have seen with the mobile phone. Do you still remember that discussion where we're talking about mobile phones is kind of like grilling our brains? Now we all have a phone. We all love it and we all hate it. After BMI is going to be approved safe from the government, and then we can pretty much guess that the same adoption curve, maybe even faster, will happen as we have seen in mobile phones. The next big application will be augmented vision. Scientists have already successfully managed to fire single neurons inside our visual cortex that trigger our retina. So when we fire these neurons, we see actually right now when we do that, we see a white dot at the spot where the neuron would fire. Now, a couple of years down, it is thinkable that we can actually project colors, and sooner or later we can project images. And that would lead to basically the opportunity to have an AR extra layer on top of our visual area. That, for example, we could look at a person and then we would see the age, the name, and maybe the Twitter feed of that person. Or we could take a wall and we say, I want to have a screen on this wall, and whenever I look there, I'm going to see the football game playing and the sound, I'm going to hear it, but everybody else who's looking at the wall will just see the normal wall. We have already figured out how to turn analog signals inside of our brain into digital data. With the help of clever apps, we can save video, audio, 360 files, and as well, we can also invent new file standards that we would use for whole experiences, including feelings, smell, temperature, skin sensitivity, and other things, maybe higher level things like thoughts like fear, joy, love, or other things. These experiences can then be stored digitally onto drives or even in the internet. Thinking this further, we could use brain stimulation to project these data back into the brain. For this, we would need the original analog data that we have seen when the neurons were firing, and then stimulate that back the same way. Depending on how many neurons we can actually reach, the playing experience will be better or worse. We could, ideally, of course, we would like to talk to the entire brain and the entire nervous system. Imagine how would your relationship to your mom be if you, as a young teenager, would have felt the pain that she had when she was giving birth to you. At the moment, humans get 5 senses. Some say we have 6. With a BMI, external sensors can give indirect or direct input into the brain. For example, we could have ultrasound, radar, infrared, and so on, augmenting our reality. With a radar, for example, we could feel a car that's coming up from behind us or from behind trees. Today, if we want to exchange data with somebody who is not nearby, we would call. In that case, we could hear, talk, and maybe see if it's a video chat. With BMI, it will not only be possible to talk without any headset. If we allow, we can also sense with other people's senses. We can taste the steak that he or she is eating. We can feel the wind on her skin. We could feel feelings, maybe even, of that person, like excitement, love, hate, or disappointment. This will be possible with very granular firewall settings that allow users to set read and write settings for different parts of their brains and for different level of thoughts. Since this enables us to be a passenger, at least for a while, into another person's body, the floodgates for all sorts of entertainment are open. Influencers will now be able to allow their followers full reading access into their sensory output, while performing extreme sports, expensive wine tasting, bar fights, adrenaline games, and of course, a lot of porn. These experiences will be far more real than what we have today with VR, because the sensory output of the influencer will be directly trigger the neurons in the viewer's brain. And this, of course, will not only revolutionize YouTube. Unique experiences, knowledge, and know-how is something that we value very high in our current society. In times of BMI, that will stay the same. But the monetization model will be fundamentally different. A helicopter pilot, for example, with 30 years of experience could upload his experience as a data set onto something that is called an experience market. And then he puts a price tag on that. Now, millions of people would like to fly like him and want to buy his experience. With this, knowledge will become commodity. And over time, more content is available, that price will go down. That means that universities of the future will be disrupted by knowledge markets and app stores. Just like the mouse in Nicolela's experiment knew which lever to push to get the water, we will also be able to learn, or at least know, motorical skills, thinking practices, and fact knowledge. And of course, if we have a market, we also have a black market. So I leave that up to your imaginary world, how that goes around. One thought that I haven't mentioned is actually the reason why Elon Musk is in this space. He talks about that quite frequently on media, so I don't go too deep into that. But the idea is that the intelligence of a general AI would surpass the intelligence of humans. And the AI will keep growing exponentially. Then we will be very soon in the position that the tiny little ants have in front of us today. If they crawl in front of our house, we don't mind. But if we want to build another house there, they gotta go. Elon's opinion is that if we got a high bandwidth interface to merge our brains with the AI, we may have a slight chance to survive on this or another planet. Latest here, we should actually start talking about reality and ask what reality really means. If we assume that all thoughts, memories, and experiences of our realities are nothing else than electrochemical processes going on inside our brains, reality will now altered, argument, and created. Our feelings and our feeling for reality may get a lot more fluid. We may get used to the fact that there are many different realities that we can live in, or that we have to deal with. Besides living the reality of another person, we could also live the reality of our favorite animal. We could also as well log into robot bodies that live on the other side of the planet, on the moon or on the Mars, and remote control them as if they would be our own body. What is reality then? If we look into the past, we can see that our generation already identifies a lot more with the little kid in Africa. Our media behavior and possibilities brought us humans much closer together on this planet. With the age of mainstream BMIs, large parts of the population have seen other people's love, felt their pain, maybe even merged their brains together for a while, and we are highly likely to grow closer together as a species. I would not quite say that we become like the Borgs from Star Trek, but there will be definitely a lot more we than me. How much individuality stays in every person is yet to be found out. I hope I could open your eyes a little bit for this field that seems to be to have so much impact on our future, but that I don't see being discussed that much about really yet, even though the technology is already there. I hope this sparks interest, and I hope you join in the discussion in your society, and not just inside of the boardrooms of a handful of startups that actually choose the face for us. Connect on LinkedIn if you're interested in me, or connect on Twitter or on the website if you're interested in BMIs and their development. Thank you very much.